Okay guys, in this next video we're going to be talking about the last section from this chapter. I'll be talking mostly about units, so we'll go to that section. I'll talk generally about units at first, and then what I'll show you is this factor label approach involving mathematical calculations that have units in them. And we'll do some dimensional analysis type of calculations as well and practice our unit conversions, which are very important in chemistry. So just some general comments. The standard unit system used in science is the SI unit system, which is the International System of Units. It's based on powers of 10, so we call it a metric system, and it involves various SI prefixes for representing different powers of 10. Moreover, there's also 7 base units that we use. Contrast that with the older English style system, which still has common usage in many countries, or several countries at least, including the United States. So we'll also say a few words about that. And we're going to do some unit conversions back and forth between the SI unit system and the English system, just because English units are still used in this country. Well, here are the 7 base units that are used in the SI unit system. So for length, the SI unit is the meter. For time, it is the second. For electric current, the unit is called the ampere. For brightness, luminous intensity, the unit is called the candela. For mass, it's not the gram, it's called the kilogram. Okay, so we actually use a prefix for the base unit of mass, which is different from all of the other base units. In terms of temperature, temperature is measured in units of Kelvin, and our counting unit, that is the amount of substance, is called the mole. And we'll have a lot more to say about that in this course. The next slide shows the different SI prefixes that we use. And so you see here different powers of 10 are represented by different prefixes, and these are the symbols for those prefixes. And I encourage you to commit 10 to the 15 through 10 to the minus 15 to memory. So you need to know femto through peta by heart. You need to know the prefix, the symbol that's used, and then the power of 10 that is represented by that prefix. And so this is just something that you have to commit to memorizing. Hopefully you have many of them memorized already, but I do think it's important for you to go through this and to learn those SI prefixes. As you'll see in the next example, you need to know those prefixes by heart in order to work certain types of problems. And so in this problem here, we're given a number of quantities, and we're being asked to choose an appropriate SI prefix to express that quantity. So I'm going to pull up my paper here, and we'll just go through these. So for part A, 1.84 times 10 to the minus 9 meters would best be represented using the nano prefix. So that times 10 to the minus 9 part is represented by the nano prefix. In part B, we have 5.6 times 10 to the minus 12 seconds. That should be written as 5.67 picoseconds. So 10 to the minus 12 is a pico. For part C, we have 10 to the minus 3 as the exponent, and so that'll be 7.85 milligrams. For part D, we have 10 to the plus 3, and so that would be 9.7 kilometers. So 10 to the 3 is the kilo. For part E, we could actually go 2 different routes. We could write this as 0.732 milliseconds, or we could write it as 732 microseconds. And by the way, this funny letter here, this is a Greek letter mu. It looks like a U with a long left-hand leg there. Part F. Again, we could go two different routes. We could write this as 1.54 nanometers or 154 picometers if we want it. So what I've done here is I've taken the different powers of 10 that we have, and then I have used the appropriate SI prefix to denote that power of 10. Next up, we are going to talk about just some of the individual quantities that we will encounter in this course. And so length, which is measured in meters, I just wanted to say a few words about that. If you're not accustomed to thinking it in meters, a meter is about 3 1/3 foot. We'll also be talking about distances at the atomic scale, so very small objects. Their distances are often expressed in terms of angstroms. And so this is that funny symbol that you see here, this A with the circle over the top. That represents 10 to the minus 10 meters. So there's no SI prefix for 10 to the minus 10, but the term angstrom refers to 10 to the minus 10. And so we often express bond lengths, that is the distance between two atoms in a chemical bond, in terms of units of angstroms. Another common unit that we will use is the nanometer. Nanometers are, 1 nanometer is 10 to the minus 9 meters, and that's also 10 angstroms. Just a reminder, the SI unit of mass is the kilogram. It actually has the prefix built into it, not the gram. And just for your reference, 1 kilogram is about 2.2 pounds, so a little over 2 pounds. In terms of units of time, seconds is the SI unit. And for small time scales, we do use SI prefixes. So it's common to see quantities reported in milliseconds, microseconds, nanoseconds, even pico and femtoseconds, depending on what type of experiment you're talking about. However, at long times, we don't use the larger SI prefixes. We revert back to minutes, hours, days, weeks, and years. And so you need to know that 1 minute is 60 seconds, 1 hour is 60 minutes, one day is 24 hours, etc. So just keep that in mind. We typically use these terms for long times, but we use these terms for short times. The unit of temperature. Here you see a graphic illustrating 3 different temperature scales. The SI unit scale for temperature is the Kelvin scale. Also, what finds common usage in science is the Celsius scale. And then in countries like the United States, we also use the Fahrenheit scale, typically when talking about weather. For science and for this course, we really only need to focus on the Celsius and Kelvin temperature scale. The Celsius scale is based upon water. That is, the freezing point of water is set at 0 degrees Celsius, and the boiling point of water is set at 100 degrees Celsius. And so there are 100 degrees Celsius between freezing water and boiling water. The Kelvin scale is similar in the sense that there's 100 degrees Kelvin between freezing water and boiling water. However, the scale is shifted, and then that freezing point of water occurs at 273.15 Kelvin, and the boiling point of water occurs at 373.15 Kelvin. So really, we only need to focus on those 2 temperature scales. On this slide, I've included conversion factors for converting between both Celsius and Fahrenheit and Celsius and Kelvin. The ones that we need to focus on in this course are the temperature conversions between Celsius and Kelvin. And so this is something that you need to know by heart. You need to be able to convert a temperature in Celsius to a temperature in Kelvin. You do that by adding the number 273.15. You also need to be able to go the other way. To calculate the temperature in Celsius from the temperature Kelvin, you need to subtract 273.15. So this conversion is something that you need to be able to do without assistance. A tip for you: the temperature in Kelvin can never be a negative number. It should always be a positive number. And so keep that in mind when you're calculating a temperature in units of Kelvin. If you get a negative number, that means you've done something wrong. Here is an example problem where we're being asked to calculate, convert different temperatures. We are going to focus on part C here, since this one involves just the Celsius to Kelvin conversion. We are given a temperature of minus 78 degrees Celsius, and we're being asked to convert that to units of Kelvin. What you do is you take the temperature in Celsius, the minus 78 degrees Celsius, and you add to that 273.15. Okay, and you use that to calculate the temperature in Kelvin. And I'm getting 195. You'd get 0.15 Kelvin, and then if we want to keep the number of sig figs the same, or if we want to use our rules of sig figs, we would round that down to 195 Kelvin, like that. Okay, so make sure that you can go back and forth between Celsius and Kelvin. On this slide, what I'm presenting are different derived units. So you can use the base units, the base SI units, and combine them in different ways to give you new units. And so if you take meters squared, that gives you the quantity area. If you take meters cubed, that represents a volume. Meters per second, so meters divided by seconds gives you a speed. Meters per second is an acceleration. Here is the SI unit of force, kilograms meters per second squared. It's also called the Newton. It's named after Sir Isaac Newton, and it's represented by the symbol capital N. So this collection of base units also goes by the symbol N for Newton. For pressure, we have this collection of units, which is called the Pascal, and we'll work with pascals when we get to gases. When we do the thermochemistry portion of the course, we'll work with units of joules, so kilograms meter seconds per meter squared per second squared. It represents energy, and we call that the joule. We'll also work with heat capacity in this course, which has units of joules per Kelvin. In the second semester of general chemistry, you'll encounter the quantity entropy, which also has units of joules per Kelvin. We'll talk a little bit more about density in this video. The SI units of density is mass per unit volume, so kilograms per meter cubed. And there's all sorts of other units here, so we'll encounter several of these in this course later on. So just have a look at these. You don't necessarily have to memorize all of them, although we will be memorizing a few of them in different problems that we have to work out. So we'll get to them all in good time. A few words about volume. The SI unit of volume, the cubic meter, is actually a very large volume, much too large for normal lab work. Instead, we use the unit liter, which is actually a cubic decimeter. Recall that the SI prefix deci means 10 to the minus 1. And so a cubic decimeter is 10 to the minus 1 meters cubed. So 1 liter is 1 cubic decimeter, which is 10 to the minus 3 cubic meters. So 1 liter is a lot smaller than 1 meter cubed. It's about a thousandth of a meter cubed. We often work in milliliters as well. 1 milliliter is equivalent to 1 cubic centimeter. And so here's that conversion factor here. 1 milliliter equals 1 cubic centimeter. And that would be 10 to the minus 6 cubic meters. And so the diagram here, this is meant to represent a cubic meter. And this little corner here, this would be 1 liter. And this little tiny green corner of this one would be a milliliter. And a milliliter is about the size of a dime. roughly speaking, depending on what liquid you're talking about in terms of its volume. So this just kind of sets the scale that, a cubic meter would be too large to work with. Really, we work with liters and fractions of liters all the way down to the milliliter scale. The unit density. So density is the derived unit. It's mass per unit volume. Okay, and so it has the SI unit would be kilograms per cubic meter. However, we don't usually use that in chemistry. Rather, we'll often use grams per milliliter when we're talking about the density of liquids and solids. Or if we're talking about gases, we'll often use grams per liter. So these two units are more commonly encountered in chemistry than the kilograms per cubic meter. To give you a sense of what a typical density would be, the density of water at 4 degrees Celsius is about 1 gram per milliliter. So in that dime-sized amount of liquid water, it would have a mass of 1 gram. That amount of water would. One of the cool things about density is that different substances have different densities. And so in a sense, you can use the density of a substance as a way of characterizing that substance. It's a property of that substance. You have to be a little bit careful, though, because density does change with temperature, and it can change with pressure as well. So you have to measure the density at a particular temperature if you want to compare it to a table of densities or something like that. But anyway, one of the things that we need to be able to do is to use the density of a substance to make conversions between mass and volume. Okay, and so here is the formula definition of density. So D represents the density of a substance. The density is equal to the mass of a sample divided by the volume of that sample. So you can use this formula to calculate the density. You measure the mass of your sample and divide it by the measured volume of the sample, and that's going to give you the density. Now, you can also rearrange this equation in different ways. And so here I rearranged the equation to give us mass equals the density times the volume. So I've moved the volume from the denominator on the right-hand side to the numerator on the left-hand side, and then flipped the equation to give me this equation. Here, if you knew the density of your liquid and the volume of the liquid, you can use that to calculate the mass of the liquid. So you can use density as a conversion between volume and mass. Or you can rearrange the equation yet again and write it as the volume equals the mass over the density, and then you can use this equation to convert the mass of an object, given the density, to the volume of the object. So the density provides a way of converting between mass and volume. And so I recommend that you memorize this definition of density and its units, and then you need to be able to algebraically rearrange this equation to do these different conversions. And we are going to do some example problems. If not right now, we'll do it in a few slides. Oh, it looks like we'll do one right now. So let me pull up my paper here. So we've got a piece of metal wire that has a measured volume of 20.2 cubic centimeters, and it has a mass of 159 grams. We're told that this metal is either manganese, iron, or nickel, and someone has provided us with the densities of these different metals. And so what they want us to do here is to calculate the density of the metal and then identify which metal do we have. Okay, so for part A, we need to use the density formula, which is mass divided by volume. And so that's going to be 159 grams divided by the 20.2 cubic centimeters. And so we will run that through our calculator. And I'm getting 7.87 grams per cubic centimeter. And so looking at the given densities we have, we would conclude that this metal is made out of iron, most likely. So you can use density to identify a substance. Here we have another example. It's a different type of problem. I believe we're going to be using density as a conversion factor here. And so we have an experiment that wants 43.7 grams of isopropyl alcohol. And instead of measuring out the mass of the isopropyl alcohol, we will dispense the isopropyl alcohol using a graduated cylinder, which measures volume. If we know that the density of the alcohol is 0.785 grams per milliliter, what volume of isopropyl alcohol do we need in order to deliver 43.7 grams? So what I'm going to do is I'm going to take the density formula. This problem is asking us to find the volume. We know the mass that we want, and we know the density, but we want to find the volume. So I need to rearrange this equation. I'll move the volume over, solve for volume, and I'll move the density down below. So I've moved the volume over and the density down. We'll plug in the mass that we want, 43.7 grams, and we'll divide that by the 0.785 grams per milliliter. Okay, we'll run this through our calculator. And I'm getting 55.7. And that would have units of milliliters. Notice what happens in the units here. You see that the grams cancel, which is going to leave us with 1 over milliliters for the units. And whenever you take 1 over a fraction like this, it brings the denominator here into the numerator. In part B, we have another problem. We're talking about ethanol. We're given the density of the ethanol, and they want to know what would be the mass in 32.5 milliliters of ethanol. So here, we'll take the density formula. This time we know the volume and the density. We want to find the mass. And so I'll rearrange this equation as density times volume. Plug in the density, 0.789 grams per cubic centimeter, and then we'll multiply by that volume. Recall that 1 milliliter is equal to 1 cubic centimeter, so 32.5 milliliters is also 32.5 cubic centimeters. You'll see that those cubic centimeters are going to cancel out, and we're going to be left with grams. So I'm getting 25.6 grams out of that calculation. Okay, so you want to be able to use the density formula, and you need to be able to rearrange it in different ways. So given any two quantities in this equation, you need to be able to find the third quantity. Right. So in this next section, we'll talk more about units and doing unit conversions. Okay, so as it says at the top, your measured quantities and your derived quantities when you're doing scientific work, they all need to be reported in the proper unit. And it's useful to think about units in your problem solving because you can often use the units to help you solve the problem. And what I'll be showing you is this factor label approach to doing unit conversions, which provides us with a method for keeping track of units. It's a little time consuming in the sense that it involves more writing. However, it makes it a lot easier to spot errors in your calculations, and of course it can help you with getting the correct units in your problem solving. So it's a good thing to use this factor label approach. This slide shows you two examples of doing a simple one-step unit conversion. On the left, we have an abstract example where we're not talking about anything in particular, just a generic unit conversion. most people tend to favor this practical example where we're being asked to convert 3.5 inches to centimeters. So this is something real that you can think about, much easier than this abstract example. So I'm just going to focus on this side here. So if we're being asked to calculate or to convert 3.5 inches to centimeters, what we need to know is the conversion factor between inches and centimeters. And so this statement right here, this statement of equality, is a conversion factor. It says that 1 inch is equivalent to 2.54 centimeters. Okay? So what we want to do is to take the 3.5 inches and we want to write it in terms of centimeters. And so here's how to think about how this works. Imagine taking 3.5 and multiplying it by the number 1, okay, with no units. So if you multiply anything by 1, you just get the same thing back. So we don't want to change the measurement, we just want to change the unit. And so this is what we're going to utilize. And the question is what are we going to use for this value of 1? And that's what I'm showing you here in this second equation above. If you take this equation and divide both sides by 1 inch, that includes the value and the unit, you get this result here, which states that 1 equals 2.54 centimeters divided by 1 inch. This is the conversion factor that we need to multiply inches by in order to get units of centimeters. Okay? And so that's what I'm doing here. I'm substituting in for this 1, I'm substituting in this conversion factor. And I'm allowed to do it because this does equal 1. You'll see that the inches cancel out, right? The inches in the numerator cancel the inches in the denominator here, and then we're left with units of centimeters after we multiply 3.5 times 2.54. And so that's the secret to doing unit conversions. You always want the unit that you have to be canceled in the denominator of the conversion factor so that you're left with the unit you want. So units you want in the numerator, units you have in the denominator. That's how you choose what to put here in order to do the unit conversion. And we're going to practice this a couple of times in the rest of this video. So here we're going to be doing some fairly straightforward SI to SI unit conversions. That is, we're converting from one SI unit to another SI unit. Okay, so we've got some nitrogen gas, and we have 243 milligrams of that gas. So the milligrams right here. We're being asked to convert that to kilograms. Okay, and so this is the strategy that I like to follow for these SI to SI unit conversions. We are given milligrams. I like to go to the unit with no prefix first, grams. So I'm going to get rid of the milli and go to grams. And then I'm going to do a second unit conversion to kilograms. So we're going from one SI prefix to another. That's what I mean by SI to SI. So here's how you need to know the prefixes in order to do these problems. There's no getting around that. But here's how you actually carry out the calculation. So we would take the 243 milligrams, and we would ask ourselves, okay, how do I get that from milligrams, how do I get that to grams? Okay, so you want to have milligrams on the bottom, and you want to have grams on top, right? So it's the unit that you have needs to be in the denominator, and the unit that you want needs to be in the numerator. And so now we got to figure out what numbers need to go here. And so this is where the SI prefixes come into play. You need to know the SI prefixes. Milli is smaller than a gram, so we would have 1 gram up top, and we would have 1,000. I'm going to write that as 10 to the 3 on the bottom. Okay, so this is going to carry out the conversion from milligrams to grams, and then I'm going to put right next to that the conversion from grams to kilograms. So here we've got grams. We want to get rid of the grams and have kilograms. So we're going to put kilograms in the numerator, and we want to cancel out the grams, so we put the grams in the denominator. And so now we want to ask ourselves, what numbers do we want to put here? Well, we know that kilo is much larger than a gram, so I'm going to put 1 gram here, and I'm going to say, well, actually I should do it the other way. I'll put 1 kilogram here and 10 to the 3rd grams there, right? You need 1,000 grams in a given kilogram. Okay, now we see that the milligrams will cancel and the grams will cancel, and we'll be left with kilograms. Okay, so this is going to wind up being 243 times 10 to the minus 6 kilograms. And I'm going to put that in proper scientific notation. I'm going to write that as 2.43. I've made the significand smaller, so I need to make the exponent bigger by a factor of 10 to the 2. And so we're going to do 10 to the minus 4 kilograms. There you go. Let's do the next one as well. Here we're given a distance. So in part B, we have a distance between two oxygen atoms is expressed in units of picometers. And we are being asked to convert that to millimeters. So we need to go from picometers. I like to go first to meters and then figure out what the conversion to millimeters would be. So it's a 2-step conversion process. So start with what you have, 121 picometers. And what we want to do is multiply something that will cancel the picometers. So we want to have picometers in the denominator. We want to have meters in the numerator. And so the question is what numbers do we want to put here? So 1 meter is a lot larger than a picometer. And if you'll recall from our discussion of the SI prefixes, this should be 10 to the 12. There are 10 to the 12 picometers in every 1 meter. So the picometers are going to cancel and we'll be left with meters. Now we want to do the meters to millimeters conversion. So we want to cancel meters and we want to have millimeters in the numerator. Millimeters are smaller than meters, and so for every meter we have 10 to the 3, 1,000 millimeters. So our picometers are going to cancel, the meters are going to cancel, and we'll be left with millimeters. And so this is going to be 121 times 10 to the minus 9 millimeters. And again, we'll want to write that in proper scientific notation. We're going to make the significand smaller by 2 decimal places, so we need to make the power of 10 bigger by 2 decimal places. And so 1.21 times 10 to the minus 7 millimeters. Okay, so you want to make sure that you can do these SI to SI prefixes. You'll want to practice using the end of chapter problems in the OpenStax textbook. Let's see what we have next. Oh, here we have the volume conversion. So this one's kind of interesting. Let me get a fresh piece of paper for it. So volume calculations, volume conversions are a little tricky. There's a trick to them. You need to cube your conversion factors. So let's go over how to do that. So someone has proposed that we convert the volume of the world's oceans, 1.35 times 10 to the 9th cubic kilometers. Let's convert that to liters. Strange request, but we will try to accommodate them. So here what we need to do is go from cubic kilometers. I recommend going to cubic meters, so that should be a 3. And then we're going to convert that to cubic decimeters, which is equivalent to liters. Okay, so that's the conversion strategy that we're going to follow. but there is one trick, and that is we need to cube our conversion factors. So let's start with what we're given. 1.35 times 10 to the 9th cubic kilometers. Okay, so that's what we have. And we want to go from kilometers cubed to meters cubed. Okay, so we want to cancel the kilometers, and we want to have meters. Now, 1 kilometer is a lot larger than a meter, so it would be 1 and then 10 to the 3 in the numerator. But this is the conversion for distance, not volume. And so here's where the trick comes in. You need to cube the conversion factor. So instead of being 10 to the 3rd, it's going to be 10 to the 3rd power, or 10 to the 9th. Next, we'll do the conversion from meters to decimeters. Okay, so we'll have meters in the denominator, and we want decimeters in top. Now, a decimeter is smaller than a meter. So for every meter, there will be 10 decimeters. And again, we need to cube that conversion factor. And then the final conversion factor would be that for every cubic decimeter, you have 1 liter. That's the simple one for this last part. Okay, so this is the calculation that we want to perform. We see that the cubic kilometers are going to cancel, the cubic meters are going to cancel, and the cubic decimeters are going to cancel, and we'll be left with liters. So this will be 1.35 times 10 to the 9th. This part is going to be 10 to the 9th. This part is going to be 10 to the 3rd. And now that we're multiplying all of these, we can simply add the exponents. So we've got 9 plus 9, it's going to give us 18, 19, 20, 21. And that's going to have units of liters. Okay, so when you do volume conversions, you want to cube your conversion factors. Let's try another one. Let's do part B. Here is a microscopic version of the same problem. Here we're given the volume of the unit cell of gold metal, and we're told that that volume is 67.6 cubic angstroms, which is going to be very small, and we're being asked to convert that to liters. So one thing that we're going to need to know is that 1 angstrom is 10 to the minus 10 meters. Okay, so that's the conversion factor that we'll need. Let's set up the problem. We are going to go from cubic angstroms. I recommend going to cubic meters, and then going to the cubic decimeters, which is equivalent to the liter. Okay, so starting with the 67.6 cubic angstroms, we're going to take advantage of this conversion factor here, which we can write 10 to the minus 10 meters per angstrom, and that needs to be cubed. So that's going to do this first conversion, and then we want to go from cubic meters to cubic decimeters. There are 10 decimeters for every 1 meter, and we need to cube that. And then the trivial conversion, 1 liter equals 1 cubic decimeter. So the angstroms cubed are going to cancel, the meters cubed are going to cancel, the decimeters cubed are going to cancel, and we'll be left with units of liters. So we'll take the 67.6, we'll have 10 to the minus, that'll be 10 to the minus 30. This will be times 10 to the 3, and our final unit is liters. So this is going to be 67.6. This will be times 10 to the minus 27 liters. And then we should probably adjust this. We've made this smaller, so we need to make this one a little bigger. That would be our final answer in proper scientific notation. Okay, for this last part, we are going to do a few conversions between the English system and the SI system. And so here is a table. You don't have to memorize anything from the table, really. For example, in the assessment I give you, any of the conversion factors that you need to use will be given to you. So this isn't a memorization slide. I just need to show you some conversion factors. If you're doing a problem involving length, you need some way of converting from SI units to the English system. And one way to do that is to use this conversion factor between centimeters and inches. Okay? You'll notice that it says in parentheses here that this is an exact conversion factor, which means you don't need to consider the sig figs involved in this conversion factor. You're to treat this 2.54 as having an infinite number of significant figures. Likewise, all of these integer-based conversion factors are exact as well. If you're doing a problem involving masses, you may take advantage of the conversion between kilograms and pounds. Okay. If you're doing volume, let's see, it looks like the conversion that we have here is between liters and quarts. And then we've already discussed these units for time, and most people, just about everybody already has these conversion factors memorized, so we don't need to worry about those. Well, let's take a look at a problem involving US to SI unit conversions. So in this first problem, we're being asked to calculate the number of centimeters that there are in 6.5 miles. And so here is the strategy that I recommend that you follow for this problem. You go from miles to feet, and then from feet to inches, and then from inches you'll go to the centimeters. So this is the strategy that we want to follow. And you would make use of the conversion factors that are here on the previous slide. So you would use this conversion factor to convert from miles to feet. You would use this conversion factor here to convert from feet to inches, and then you can go from inches to centimeters. Okay, so we'll start with what we have, the 6.51 miles. We want to cancel the miles, and so there's 5,280. Oops, I got that in the wrong place. There are 5,280 feet in 1 mile. So I caught myself. I would have the wrong unit in the denominator. I want to cancel the miles so that I have feet. Then to do the, and I'm just going to check the conversion factor. Yeah, I got it. To do the conversion from feet to inches, we would put feet in the denominator. So we'll have 1 foot down here, and then we'll put 12 inches up top. Okay, so that's going to cancel. And so we'll be at inches now. And now we'll do the conversion between inches and centimeters. There are 2.54 centimeters in every inch. Okay, and so the inches will cancel, and we're going to have centimeters. So we'll run this string of numbers through our calculator. And I'm getting a large number, of course. I'm going to write this as 1.05 times 10, and let me count the decimal places here. We've got 3, 6, times 10 to the 6 centimeters. And that makes sense, right? 6.51 miles is a long way. A centimeter is a very short distance, and so of course there's going to be a lot of centimeters in that large of a distance. Let's see. Using the definitions of 1 inch equals 2.54 centimeters and 1 yard equals 36 inches, obtain the conversion factor for yards to meters. Well, why don't we interpret that to mean convert 1 yard to a meter? So our goal will be to go from yards to let's see, yes, to inches, from inches to centimeters, and then we'll go from centimeters to meters. And what they want to know is what is the overall conversion factor here. So we'll just start with 1 yard. And then we'll do 1 yard equals 36 inches. And there are 2.54 centimeters per inch. And then now we want to do the SI unit conversion from centimeters to meters. There are 10 to the 2 centimeters in 1 meter. And so the yards will cancel, the inches will cancel, the centimeters will cancel, and we're going to have units of meters. So we'll run these numbers through our calculator. And we find that 1 yard equals 0.9144 meters, and that is an exact conversion factor because all of these numbers are interpreted to be exact. Now they want us to use that conversion factor to find out how many meters there are in 3.54 yards. So we'll take 3.54 yards. We'll use our conversion factor. We want the meters up top and the yard down below, so those cancel. And I'm getting 3.24 meters. So that's the last slide I have for this video. We'll start with the second chapter of the textbook in the next video.